Okay, this is video 2.7, which deals with something we're going to call an antiderivative. You might have guessed that's the opposite of a derivative. We know at this point how to find velocity given an expression for position. We take the derivative. But what if we're given an expression for the velocity and asked to find the position? And that's actually a much more common sort of physics problem that you deal with in everyday life. So here's an example. Let's say v as a function of t is equal to 16t squared. Now we can tell from this, because it's got that t squared in there, that it's not constant acceleration, so we can't use the kinematic equations. And so what we've got to do is we want to find a function, x of t, such that dx dt equals 16t squared. And so we've got to ask, what function has a derivative that is 16t squared? Well, the first thing you say is, well, we've noticed a pattern that when you take the derivative of something that's t cubed, you get something that's t squared. So we're pretty sure that x of t is going to have a t cubed somewhere in it. Now we've got to just figure out what number goes on the front. And we'd say, well, when you go from t cubed to t squared, you multiply by 3. So we've got to have 16 divided by 3. And just, to make sure that that's correct, we'll check our work, dx dt, use the power law, we get 16 over 3 as the constant out front, times 3 times t squared, yep, we get 16t squared. So we're almost done, not quite though, because that's not the only function that has that derivative. What about if we change it to add 1? What's the derivative of that? Work it out, you'll find that the derivative of this function is also 16t squared. And so when you do this antiderivative, you have to add a constant, c, where c is some undetermined constant, and normally its value will be set by the initial position. In this case, c is wherever this starts out at, because the velocity doesn't tell you what the position is, it only tells you how the position is changing. So that's why we need the constant. And that's what we call an antiderivative. The good news is there are many shortcuts for the antiderivative as well, and they correspond to things that the shortcuts for the derivative. The first one is the sum rule. What the sum rule says is that the antiderivative of the sum is the sum of the antiderivatives. Now, in order to write this out mathematically, we need to introduce another symbol, which is the antiderivative or integral symbol. So what we would say is that x of t equals integral v of t dt. Where this integral just means opposite of the derivative. And this dt is the variable of integration. Not a terribly important thing at this level, but you should always include it, lest you make the mathematicians angry. So back to this. If we write this mathematically, we can say that the integral of x of t plus y of t dt equals the integral of x of t dt plus the integral of y of t dt. It's very, very useful and not terribly difficult to remember. Second one is the power law. This one is also extremely useful, and it's just the opposite of the derivative power law. What it says is that if you have the integral of x raised to the nth power dx, notice that this is not x of t, this is just x, it's a variable, not a function, is equal to 1 over n plus 1 times x to the n plus 1 plus c. Always got to have that plus c. And this applies to any value of n except for n equals -1. So some examples of integrals you could, or antiderivatives you could solve with this rule. Square root of x dx. In this case, n is equal to 1/2. 1 over x squared dx. In this case, n is equal to -2. So it's a very, very useful thing. Now the next question is, what if n equals -1? Well, the integral of x to the -1 dx equals the natural log of x. And to keep the mathematicians happy, you have to put that in absolute values because natural log blows up if you try to put a negative number into it. So memorize that power law. Also, this thing with the logs is very, very common in physics, so memorize that too. Now the next three will go by very quickly. Sine, cosine, exponential. The integral of cosine x dx is, guess what? Pardon me. I will just reorder that. Okay, there we go. Integral of cosine x dx is sine x, because remember the derivative of sine is cosine. The integral of sine x is negative cosine x. Oh, and we've got to add the plus c. Always remember that. It actually is important. And then exponential, remember the exponential function is its own derivative. It is therefore also its own integral. And it's very easy. So those are the antiderivative or integral shortcuts you need to know. The sum rule is easy. The power law is less easy but tremendously important. Cosine, sine, exponential, all fairly easy to remember. The important thing is this negative sign and that one. At this point, you should be able to do many of the problems in your homework assignment, and what I'm going to check tomorrow are problems 1 through 3 on that assignment.